All right, so this is joint work with Sean Kennedy and Gordon Wilfong at Bell Labs. This is work really on secure computation and how to evaluate Boolean circuits securely. So I'll motivate the problem, what really we're solving, and then show a heuristic, how to reduce circuit size in certain scenarios that make sense, and then explain how this, how some tools in garbled circuit and GMW support the improvement that we make. Okay, so this is all about SFE, secure function evaluation. What is it done? How do you do it today? Given a function f that you want to compute, the most concretely efficient way in most cases is that you generate a Boolean circuit that computes the function f, and then you run a garbled circuit or a GMW. And people really squeeze a lot of efficiency of those approaches. It's really, really hard to get even a small, like several % performance improvement. There is much less work on the circuit representation of the function that is being computed, and this work is kind of in this domain. Circuit representation a lot of the time is really inefficient, and there are several kind of major inefficiencies that I could think about, and some of them are being addressed and some of them are not. So random access is one thing. If you have an array and you want to access a random element in the array, you have to read the entire array, right? So people work a lot on this, and I think ORAM, this whole direction is really important. It's really fundamentally changing asymptotics of secure computation. And then you have loops. I don't know what you can do about that. And today I'll focus on what happens if you have conditional statements, right? So today, if you have a garbled circuit, okay, so when do you have conditional statements? A lot of the time conditional statements come up. And this is kind of a very simple example that I'll start with, but it will be generalized. You'll see how it generalizes to whatever you want. So let's say there is a function that you want to compute, f of cxy, where c is a choice bit or choice several bits that is given to one party, and then x is input of one party and y is the input of the other party. So in other case, you can think of it like a private policy selection. I want to evaluate one of 30 functions on our inputs, but I don't want to tell you which one. Right? And this comes up in a lot of places, in particular in the private database scenario that we were doing. Okay, so when let's say I'm the circuit generator, I'm thinking of garbled circuit. If I'm the circuit generator and I'm giving you this function to evaluate, this is the circuit that you're going to see. Right? Okay, so the circuit basically is going to be 30 of this kind of circuits, and then going to be a selection subcircuit. Right, and what you have to do, you have to evaluate all of them, and then you have to choose the output that you really are going to be using. Right. Well, so actually what really you're going to see is you're going to see this, right, where each node, this is a Boolean gate. Right, so all you see is a topology. You don't know what gate function you're evaluating, kind of in general. There is some like free XOR things, but really you can think about it this way. Right. So our idea is that, how about we do this, right? We are going to overlay those topologies if there is some kind of really cool way of putting all of this on top of each other, right, in a way that it all makes sense, that you can program each of them, right, each of the 30 ones, each one of the 30. Then all of the stuff goes away. You don't need the selection thing anymore. All you have to do is just to evaluate this one thing. Okay? And so if you could overlay it like this, then a circuit generator can program these gates, and then you get profit. Okay, so but how?
So I still need the selection bit, no?
No.
You still need C as an input. How do you know which?
If I know C, I program it right away. I give it to you. I'll tell you.
C could come as an input, no? Or C.
So let's say C is my input, and I'm doing garbled circuit. I just send you the right programming. If C is my input, if C is not, later I'll talk about when C is not fixed. C can be internal variable, and it makes a big difference between garbled circuit and GMW, the cost of this. It will be there very soon. Okay, so how do you embed, right? So optimal embedding is NP-hard. We have a theorem that says that. Naive evaluation of all of the clauses works, and that's what is done today. Is basically you just execute all of the clauses. Universal circuit also works, but it's too expensive in most reasonable cases that you can think about, because the sort of recent calculations of the size of universal circuit is about that it's 10 n log n, where n is the maximum of the circuits that has to be there. Hand designs don't really work. People don't know how to design, how to program circuits. It's like nobody really knows how they look like. It's machines that generate them. Okay, so what do? We try to exploit obviously the common topologies, and we can do a lot of things, right? Because we can insert all sorts of gates with all sorts of functionalities, like a no-op gates and pass-through gates. We can insert edges as needed, etc. Okay, so this is work with the graph theory people, and so we have to like talk in two languages, and so we start with a Boolean circuit, and then we kind of translate it into the graph domain in a very simple and natural translation. So from a Boolean circuit, we get a DAG simply by replacing, whenever you have a gate, you put a node. Okay, all right, makes sense. Also, we put some weight because we care about concrete things like free XORs and stuff like that. So we're gonna put some weight on the nodes. I'm not gonna get into more details because of the time. Okay, so our goal is that given two clauses, given two circuits or two DAGs, you want to generate a container DAG, right, such that you can implement either of the circuits. Okay, so to talk about this, we have to define what an embedding is, and this is a definition of embedding. An embedding is an embedding of a DAG D into D prime is a mapping from nodes to out arborescences. We're generalizing nodes into subgraphs in a right sense. So nodes to out arborescences, and also embedding maps directed edges to directed edges. And this embedding has to have these properties. These are natural properties that basically say that correctness will work out, and you can implement the right, the stuff that you get will have the topology that allows you to implement the regional circuit and things like that. Okay, so how we do that? Again, this is, as it turns out, this is actually very simple heuristic, but it took a long time to kind of narrow it down, and it took a long time to kind of painful implementation, but seems to be nice. So first thing to look at is that if our graphs are formulas, so that it's trees, then a straightforward dynamic programming approach gives us an optimal solution, and it's not too expensive. Okay, so all you do is just do dynamic programming with the right nodes, and then you get. And so we have a theorem that there exists an algorithm of this cost, and you can have an optimal circuit embedding D1 and D2. Okay, but formulas is too weak, is really not really interesting, right? So the general case, this is where like a lot of efficiency loss comes, but we have in terms of how close we are to optimal, but it's not, it's pretty good in our experiments at least.
But can you state what is the result? You said that this is hard to do in general,
yes,
and it's also hard to do by hand,
yes,
case by case. So
yeah, so we have the result is a heuristic that outputs container circuits that are small in size relative to the input sizes of to the sizes of the input circuits. I have a graph later, but the result is two results. One is a heuristic for graphs, and second result is secure computation related tools that allow you to run this.
It's always successful, but it's not always the optimal or good. It's not always good.
It's definitely not always optimal. I don't know what the success is.
It's correct. The correct.
Yeah. It's always correct, but the size is not. All right. So given a general circuit, so here is D1 and D2. We generate two spanning forest roots at each output node. So each of these is actually going to be a tree. So we have to drop some nodes. So we take a tree. All right, we generate a bunch of spanning forests so that all nodes are covered, right? And then make each of these make a tree. So we drop the node, the edges between between the trees, and we drop the edges inside that make them, so to make them formulas. Okay? So now we got this graph and this graph, so where this is a tree, everything is a tree, and then we do all combinations of trees, and we find whatever is best. And then we put the edges that we drop, we put them back, and we hope that everything is still okay. So everything is not still okay, we have to fix some things, and things that, the two things actually that we need to fix is that the fan-in can become too large, because when you reinsert the edges that you dropped, you can increase that. So that's important for garbled circuit, and actually, interestingly, with the new observation, it's not so much important for GMW, but we still try to keep it for fan-in too. And we solve it simply by adding an extra edge, an extra node. And also, when you reinsert the edges, cycles can happen. You don't want cycles in your graph, right? Right, because you can kind of visually see like backward-looking edges that you dropped, but then when you reinserted them, you can have a situation like that. But also, that situation is solvable by adding a few nodes. Okay, so after all is fixed, that's so that's the description of the heuristic. It's hard to say, by thinking about it, it's hard to say how good it performs. So the only thing really, reasonably you can do is just to run it. So we generated a bunch of circuits using some compiler, CBMC compiler, and we did kind of pairwise. Like we have 32 circuits, and we do a computation style and choose the right, the best pairings that we could find. And this is the empirical results. This is the number of non-XOR gates in everything. So this is the input column. So the input, there were 20,000 non-XOR gates in 32 circuits. After first round, we got 16 circuits because we did, pairwise, right? So in this 16 circuits, there were 14,000 gates total non-XOR in the 16 circuits. And so on until in the end, we get one circuit that can implement all of the 32 input circuits, and its size was about 32.
What are these 32? You did for specific 32?
For these.
So you did one circuit that it's like an if statement with 32 options, and these are the 32 options.
Yeah.
So it's a single function at the end of the day, right?
Sure. Okay. How much time I have? Not much. 8 minutes. Okay, that's not bad. Okay, so that's great, right? So it was about 6 times performance improvement. Now, what can you do now? How can, what does it give you when you go back to actually having to securely evaluate this? Okay, well, if you are in the case where you know which circuit you want to evaluate, let's say for the database policy or something, right? Then then I get 6 times performance improvement directly from that, because all I do, I'm going to generate a garbled circuit implementing all of these things. Well, now I just have to generate a garbled circuit that's much smaller, and I know what is my policy, so I just implement that policy in that topology, and I give it to you for evaluation, and you cannot tell which one it is evaluated, right? Because we know that this container circuit can implement any of the 30 circuits or the 32 circuits, right? So, so there is a direct 6 times performance improvement just from that. If in a garbled circuit, if your clause is selected by an internal variable, then you have to pay, and actually it's kind of expensive to pay. So how would you do it? So let's say there is an internal variable that kind of makes us secret share the knowledge. So there's 2 players, and we secret share the knowledge of which clause is actually being evaluated. Then you can do oblivious transfer. So the same idea, right? So all I want to do is I want to transfer the right garbled tables, right, to program that right circuit. So now I can do OT on those things, right, where the OT selection is happening based on the internal variable that is secret shared to us. So nobody knows what happened, but you get the right programming. Well, so that's not great, because to do 1 out of KOT, you have to pay basically proportional to K, because you need to, under the hood, you need to transfer all the K encryptions. Okay, so the first improvement, also the garbled circuit improvement, is that we observe that we don't need to do 1 out of KOT on the garbled gates. Instead, we are going to do 1 out of KOT on the programming string, where the programming string is very short. Let's see where we are. Here, so I'm going to do an OT where I'm going to send you a programming string where each symbol of the programming string tells you which gate is going to be evaluated, right? And then you use that information to do OT selection, to run OT and to select the right garble table. So the difference is that now we're going to have to do only 1 out of 5 OTs of garble tables, and those are the expensive OTs. And we're still going to have to do 1 out of k OT on the programming strings, but those are short. Particular, the security parameter, like the k that the computational security parameter of 100 is not going to be a multiplicative factor in the 1 out of k, and so that's a small thing.
It's now interactive. It's not.
You need to interact. But sort of the most interesting impact here is that in the GMW. So GMW and garbled circuit, they're kind of competitive, and people write some papers called GMW versus Yao, which one is better, and things like that. And this work is actually, I think, is so this observation that I'm making, and this I think it's also relevant in this kind of discussion. What is better, GMW or garbled circuit? So, all right, to recall at the very high level what happens in the GMW, when you evaluate a gate, you need to do 1 out of 4 oblivious transfer. I'm not going to tell you of what, because it's a little bit involved. And there was work with Ranjit a couple of years ago, and we observed that you can do 1 out of n for relatively small n OT for approximately the same cost as 1 out of 4 OT. Okay, and sort of the observation that we're making here, and it's relevant to the application, is that you can evaluate multi-input GMW gates roughly at the cost same as 2 input gates. So, okay, so multi-input is not going to be 100 input, but like 5 input. 5 input GMW gates will cost you the same as 2 input GMW gates. Okay, and now...
where did the 5 come from? Why 5?
It's a right kind of range.
I don't understand the trade-off. Like if 2 is the same as 5, why isn't 5 the same as 10?
Yeah, so the cost is exponential in the number of inputs, but there is a... So to do the GMW OT, what you need to do something that's proportional to the security parameter, multiplicative security parameter k, right? And then, after you've done that, you have to do something that is exponential in the number of inputs, but not dependent on the security parameter k. So that exponential in the number of inputs is growing fast, but it's starting very low, right? So like 5, 7, I don't know, something like that is the right thing. Okay, and so okay, this is the last slide, yeah. And so when we use GMW to do this, so the thing where I was talking for garbled circuit, you have to do 1 out of 5 gate table OT. So this corresponds to multi-input GMW gates, and they can be done pretty much with no overhead, or a couple of bits per gates overhead that we can say that we can ignore. And so overall, so this improvement that we bring with the circuit size due to overlaying circuits is pretty much translates directly into the total cost, which I count as communication, but computation cost is not really differing. So that improvement directly translates the same factor improvement you're going to get in GMW. Okay, so that's all. Thank you.